Today we're going to talk about instruction set architectures. An instruction set architecture is the abstract language that a microprocessor speaks. Welcome to Kopec Explains Software, the podcast where we make computing intelligible. In this episode, we're going to be discussing instruction set architectures. An instruction set architecture is the abstract language that a microprocessor speaks. The microprocessor's particular circuitry and implementation of that instruction set architecture may be unique, but a family of microprocessors that are compatible with one another will speak the same abstract language, and therefore their machine code will be compatible with one another. Programmers work in higher-level languages that ultimately get compiled to machine code, and that machine code is formatted according to the instruction set architecture.
What are some instruction set architectures that our listeners may be familiar with?
The two most popular instruction set families today are X86 and ARM. X86 was primarily developed by Intel, going all the way back to the late 1970s. Today, you'll find X86 microprocessors made primarily by Intel and AMD. You'll find them in laptops, in PCs, you'll find them in servers, and ARM microprocessors you'll find in just about everything else, from the Nintendo Switch to your smartphone, to your car, to even some supercomputers and servers today as well. ARM is starting to take market share from X86 in more and more areas. ARM itself is a company that designs microprocessors but doesn't manufacture them. And other companies license designs from ARM or the right to use the instruction set architecture. In the case of Apple, they license the ARM architecture but heavily customize it for their own microprocessors. We did a previous episode on Apple's instruction set architecture transitions, which I'll link to in the show notes. So X86 and ARM are the most popular families of instruction set architectures today. There are many individual versions of ARM and X86 and many extensions to them. For example, in the X86 world today, all of our microprocessors are 64-bit, so they use the X86 64 extension, sometimes called the AMD 64 extension. It's backwards compatible with older versions of X86, and that tends to be the case in most instruction set families. Newer versions of the architecture will be backwards compatible with older instructions. Now,
they're not compatible with each other.
Right, they're not compatible with each other. So one instruction set architecture will have machine code that's particular to it, and that machine code will not work on another instruction set architecture. For example, if you have a program that's compiled for your phone that uses an ARM microprocessor, you can't then take that program and run it on your PC that has an x86 microprocessor. And that would be even if they were running the same operating system, had all the same libraries, use the same binary format. Even if all that was true, they still would not be compatible with each other, of course, because the machine code is not compatible. The machine code is fundamentally what the microprocessor understands. So we've just been talking about ARM and X86, which are the most popular families today, but of course, there's been a wide variety of other instruction set architectures throughout the history of computing. Some popular ones from the 90s and the 00s that folks might be familiar with or have heard before, and now you know what this means, are things like SPARC or MIPS or PowerPC. Not many other instruction set architectures are still around today. One that's on the rise, that's actually an open architecture, meaning that no single company controls it, is called RISC-V. And another that is still out there, but not really that popular and kind of waning, is Power from IBM. But x86 and ARM today are really dominant. So to better understand these instruction set architectures, I think it would be great to talk about a specific example. And I think we should also talk about what an instruction set architecture really defines.
So what does an instruction set architecture define?
It defines, of course, the instructions that the microprocessor is going to need to understand. These are going to be things like add two numbers together, load something from memory, store something in memory, decide if we should jump to a different instruction right now based on some Boolean criteria. So most of these instructions actually are very simple. The other thing the instruction set architecture is going to define is the infrastructure around these instructions, such as the registers. What's a register? A register can be thought about as a very, very, very tiny bit of memory that sits right on the microprocessor, so it's extremely fast to access. And most instructions are going to interact with registers. So they might be saying, well, put this number into this register, or take this number in this register, do something with it, and then put it in another register. The instruction set architecture will also define how memory is accessed. So how do we go about getting memory from, let's say, RAM and putting it into registers? And how do we go about storing things from registers back into RAM? So that the whole interaction between instructions and memory is also laid out by the instruction set architecture.
So really, the instruction set architecture is the place where hardware and software meet.
Yeah, that's a good way of describing it. How do we actually execute the software in the hardware? This is the language that defines that. Let's talk about a very specific example. So I purposely chose a very simple instruction set architecture. It's that for the 6502 microprocessor from Moz Technologies. It came out in the late 1970s. It was used in things like the Apple II personal computer, the Nintendo Entertainment System, the Commodore 64. It was a very popular microprocessor for its time. And it was popular because it was a lot less expensive than a lot of the competing designs at the time. So things like the Intel 8080 would be multiple times more expensive, even though they offered fairly similar functionality. We're talking about a microprocessor that ran oftentimes at 1 megahertz and would only be able to access 64 kilobytes of RAM. So really, these are very primitive personal computers and computing devices that the 6502 was used in. The 6502 didn't have a lot of instructions, even for the time. Because it had such a simple design, that's one of the reasons they were able to implement it at such a low cost. And it is what we would call an 8-bit architecture. Now, you might have heard about before, like architectures being 8-bit or 16-bit or 32-bit, or most personal computer microprocessors today are 64-bit. What does that mean? That refers to the word size. The word size is the natural data length that the instruction set architecture operates on. So, for example, is it capable of working with 8-bit numbers, 16-bit numbers, etc.? Going back to the 6502, we call it an 8-bit microprocessor because the vast majority of its registers were 8 bits. And let me give you an example of what those registers are, because the 6502 was so simple, there aren't that many registers. So the 6502 had a register called A, and that was known usually as the accumulator. It's where you do a lot of the arithmetic. It's had some more general purpose registers called X and Y, both of which also were 8 bits, meaning you can only put an 8-bit number into them. It has stack pointer that's 8 bits, and that just kept track of when you jump to a subroutine, how do you go back to the last place that you were before the subroutine. You can also just put data onto the stack, push things onto the stack if you want to. And it also had a 16-bit program counter. The program counter keeps track of where in memory is the next instruction for the microprocessor to execute. This had to be 16 bits in order for the 6502, without any additional hardware, to be able to address 64 kilobytes of memory. Because as we know from prior episodes, which I'll link to in the show notes, like what is a byte? An 8-bit number can only refer to the integers between 0 and 255, whereas a 16-bit number can go all the way up to a number that's around 65,000. So it allows us to be able to talk about a lot more memory addresses when we have more bits in the program counter. So even though the 6502 is always doing math and all of its instructions basically on 8-bit numbers, it has the capability of pulling instructions from 65,000 different locations, a little more than 65,000, because the program counter is 16 bits. And then the last register in the 6502 is the flags register. And that register is used for keeping track of if something slightly out of the ordinary or something that you want to know about happened when you do a certain instruction. For example, with arithmetic instructions, if you're adding two 8-bit numbers and the result is going to be more than 255, we call that overflow. And if that happens, there's a bit in the flags register that gets marked saying, hey, I tried adding these two numbers together and the result was too big. So we might get a kind of weird result, and I want you to know that. So I've marked this overflow bit in the flags register. That's just one example of the type of thing that we use the flags register for. Now, the 6502 was really a very simple design. In fact, it didn't even have a multiplication instruction. So if you
you couldn't multiply?
You couldn't easily multiply. Now, if you think about it, multiplication is the same thing as adding the same number multiple times.
Of course.
Right. So you could just use the add instruction to do multiplication, but you have to call it several times and you have to write that code in assembly language yourself. So you have to say, I want to multiply two numbers. I actually need to basically write a loop that keeps calling add. You might wonder, why would they not include multiply? Every instruction that you add to an instruction set architecture requires additional circuitry, literally additional transistors. That might increase the cost of the design, make the design more complicated, require it to use more space, so literally be bigger because there's more transistors.
So your physical capacity could really be limits what you can do.
Exactly. Yeah. So there's physical constraints on how many instructions we can really have, and it might actually be preferable to have less instructions. The 6502 at the time wasn't thought about as a RISC microprocessor, but I want to get into the difference between RISC and CISC. These are two different philosophies of instruction set architecture design. CISC, which stands for Complex Instruction Set Computing, is a microprocessor architecture that includes complex instructions that do multiple things at once. This makes it easier for the assembly programmer because the assembly programmer has an instruction that already does what they need. They don't have to go write a bunch of instructions and combine them together to do that functionality. But it increases the complexity of the hardware design, the physical layout of the transistors, and therefore may have some implications that may make it harder to make the overall design efficient. RISC, on the other hand, which stands for Reduced Instruction Set Computing, says, you know what, let's just have really simple instructions in the architecture. That way, we can implement them as efficiently as possible, because most of the time, computers are doing the most simple instructions. The vast majority of instructions that your average program executes are going to be things like add some things together, jump to this location, simple instructions. It's much rarer to actually do those complex instructions. And those complex instructions can be reformulated out of the simpler instructions. So when we do need to do them, they might be a little more costly because we have to execute multiple of the simple instructions, but we're not going to do them that much. So it's more important that we made those simple instructions really fast. Originally, the X86 family came from the CISC world, and the ARM family came from the RISC world. In fact, ARMs originally stood for Acorn RISC Machine, where Acorn was the name of the company that came up with the ARM architecture.
Oh, I didn't know that.
Yeah, and actually they designed their own computers around that architecture, and Apple was an early investor in the joint venture to further develop ARM. So there's a lot of history there, but ARM is much newer than X86. ARM came out in the late 1980s, whereas X86 is from the late 1970s. But both are relatively old compared to the latest kid on the block, which is RISC-V, which is also a RISC architecture. In fact, that's why it's called RISC-V, right?
So as a programmer, what is something that goes through your mind or is important for you to think about when you're thinking about the instruction sets or which one you're using? Does that something that goes through your mind when you're developing something?
For the most part, you don't need to think about it at all. Because as a programmer today, you're not writing an assembly language. Assembly language is very close to the instruction set architecture. It's basically English mnemonics for the machine code. But generally, we don't write an assembly code today. And so, of course, the assembly code would differ from ARM to X86 to PowerPC to Spark. But we're writing in higher level languages. We're writing in C, C++, Java, Python, etc., right? And so we're not actually getting down to that level. And so we don't need to think about it at all for the most part. We can take our same code, hopefully, and recompile it for one architecture or another architecture. And what will differ will a lot of the time just be the availability of the particular libraries that we're using. At the same time, there is one aspect of instruction set architecture that does become relevant, especially when working in, let's call it a mid-level language like C, and that would be the endianness of the architecture. And that has to do with whether the architecture sees the first byte out of a multi-byte number as the beginning of the number or the end of the number.
Why would it see it as the end?
It's kind of an arbitrary decision that was made by the designers of the architecture. There might be some slight efficiencies in the way the transistors are laid out that would prefer one way or the other way. But for the most part, it's somewhat arbitrary. And, when we write numbers in the Arabic script that we use in the Western world, so we literally write out our digits, we always put the biggest one first, right? If I'm writing out the 91, I first write the 9, then I write the 1 going from left to right, right? But that's kind of arbitrary, right? It could have been that we designed the number 91 to be written 1 and then 9, right? That was just a decision that was made thousands of years ago, and that's just the world we're in. So they weren't constrained by some existing script when they designed instruction set architectures. And so some instruction set architectures are what we call little endian, and some are big endian. And the distinction between them is just which order the bytes are in in terms of the most significant one to the least significant one. And I used earlier the word biggest and smallest, but what would be more scientific would be to say most significant versus least significant. For example, in the number 91, 9 is the most significant digit, and 1 is the least significant digit. If the number was 127, the 1 would be the most significant digit, the 7 would be the least significant digit. But other than that, no, when you're working in a higher level language, you don't really need to think about what the particular architecture is unless you're going to have to drop down into assembly for something, or there's just going to be some libraries that are not available to you. For example, when Apple made its transition from Intel microprocessors to ARM microprocessors of its own design, there were a bunch of libraries that weren't available at first. For example, there were even some C extensions to Python libraries. So if you were programming in Python and you were using one of those new Macs using an M1 microprocessor back in 2020, it's possible that some Python libraries were not yet available to you, which was, of course, really annoying. But now, a couple of years into the transition, all of them have been ported. But as a programmer in general, you don't today think about this too much.
You don't think about it until someone's making a big transition and you have to think about it.
Exactly. So if instruction set architectures interest you, the area of computer science that you'd want to study some more is called computer architecture. Every computer science program has a class, but of course you can learn a lot on your own. And one great way to learn more about this area is actually to implement an emulator. And we did a prior episode on emulators that I'll link to in the show notes. But if you're just a layperson and you're not a programmer, then what's more interesting to follow is kind of how these architectures affect the dynamics of the semiconductor industry. For example, Intel has been having some issues the last 5 to 10 years, beyond kind of the scope of our episode today. But companies that are using the ARM architecture, which, as we've talked about, is incompatible with X86 that Intel uses, have been kind of eating their lunch. And so there's a whole ecosystem sometimes around a particular architecture. Intel's ecosystem is a lot more closed off. There's only a couple companies that use the X86 architecture, and Intel doesn't license the architecture just to anybody. Whereas ARM will basically license the architecture to anybody who can pay up. And so there are tons of companies that implement the various versions of the ARM architecture. So to recap the most important things about an instruction set architecture. An instruction set architecture specifies the instructions that the microprocessor understands and also the supporting infrastructure around it, such as how does it access memory and what are the registers that the instructions can operate on. Different instruction sets operate on different word sizes, and that's how big usually most of the registers are. And that will cause us to call one instruction set an 8-bit instruction set versus a 16-bit or 32-bit or 64-bit, etc. There are extensions to instruction set architectures for supporting newer functionality, and software compiled for one instruction set architecture is not compatible with another instruction set architecture. Thanks for listening to us this week. Rebecca, how can people get in touch with us on Twitter?
We're at Kopec Explains, KOPECEXPLAINS.
Thanks for listening, and we'll see you in 2 weeks.
Bye.